Hello, everyone. Thank you to those who reached out to request for supplementary information. So I'm going to have a brief discussion about what linear regression is and how we can use gradient descent to optimize the results. So let's have a brief recall. How can we estimate a certain model F using linear regression? So we can see here that we have a function f of x, wherein we use this function to estimate the value of y or response y given the input x. Okay, so linear regression assumes that there is an approximately a linear relationship between the features x and the response y. And this linear relationship may be written this way. We have beta naught plus beta 1x, wherein the beta naught and beta 1 are unknown constants or model coefficients. And beta naught is the intercept or bias. Essentially, in the concept of the advertising, it is the starting sales or the starting value on the other hand. So the beta 1 on the other hand is the weight or the slope that is associated with a certain feature. So in the case of the advertising again, this beta 1 is the weight that is associated with the predictor TV. So what are the roles of these parameters, beta naught and beta 1? So in a regression model, this is actually the problem. And that is actually what we need to do to estimate the value of these parameters. Because these parameters, beta 1 and beta naught, will indicate the relationships between the variables. Having these values, the model will be interpretable. So these coefficients are estimated from an existing data set or training set which is required. So suppose we have this plot. So this is simply a plot of the TV versus the sales. So as we increase the advertising budget for the TV, we can see that the sales is also increasing. And we can see here that with the addition of the beta naught or the bias, there is an additional na value here, right? So if wala tong beta naught, this line will be here. I mean, in a much lower. Okay, so suppose we have this fit, and this fit was found using the estimated na beta 1 and the beta naught. Okay, so essentially what we can do to arrive to this value is to fit the model to the training data. And once we have used the training data to produce these estimates of beta 1 and beta naught, we can use this equation or actually to predict new value for any input x. So this y hat is the prediction of y, and beta naught hat is the estimate of the bias, and the beta 1 hat is the estimate of the slope or weight of the feature. So now, in order for us to assess whether the line is fitted properly to the model, we can check for the errors, or in other words, the distance between the observed value y sub I or the actual value versus the predicted value y hat. Okay, so the error between the prediction and the actual is simply the difference in between the two. So we take the square of the error so that we can remove the negative errors. Okay, and then we do this for every point in the data set. Check the difference between the actual as well as the predicted, and then take the square and sum it all up. So that is the method of the least squares. So mean square na error that you have seen earlier, this MSE, is an example of a cost na function. So the general idea is that we estimate the parameters in regression model, and we use this cost function, such as MSE, to check how far the predicted is from the actual. Okay, so and in order for us to get a good quality model, we have to minimize this cost na function. The cost na function, again, tries to measure how big the error of the regression model is when estimating the value of the dependent variable. So essentially, as you have seen earlier, this how far away the predicted from the actual is taking the sum of those errors or the residuals is the cost of the model, and we want to minimize that. So the closer this line to the points, that means that the model is better and good enough, and we have found good estimates for beta 1 and beta naught. Okay, so when the model has multiple variables, we use multiple linear regression. So we can see here, we estimate the y with several predictors, x sub 1, x sub 2, until x sub k, wherein each of the predictors has associated the weights or coefficients, right? And you can also see here the bias. So we can rewrite it as the beta naught or the bias plus the dot product of the predictor and the predictor and each of their associated weights, right? And as an example here, we have the advertising, the data set. We have 3 features: TV, radio, and newspaper. And our response na y, wherein we try to predict the sales using these predictors. Okay, and then we can represent that into a matrix na form. Okay, so we can represent that y is equal to x beta plus the error. Okay, wherein a vector na y composing of an n by 1 na predictions is equal to the x times the beta, or the dot product of the x and the beta, wherein the x is composed of the data set, as well as an additional column composing of ones, and we simply add that one so that the dimension of the x as well as this vector na weights will be the same, okay? And we can perform dot product on it, and plus the error. So in order for us to estimate this column beta naught, so we can simply use this formula. We get the dot product of the transpose of this matrix x and x, and take the inverse of that, and then take its dot product again with the transpose of x and the y. Okay, or this y is actually the true labels or the actual labels of y. Now, the true labels of y in the training set. Okay, so we refer to the training set. And in order for us to estimate the y, we simply take again the dot product of the estimated weights beta and the x values. All right, so it is essentially the same with this previous formula, wherein we take the weighted sum of the weights beta and x. Okay, and this is just a matrix representation. So this beta naught was taken from this formula. Okay, and now in order for us to evaluate the predictions, so we can compute for the error or the residuals, which is simply the difference between the actual y sub I and the predicted y sub I hat. And in order for us to get the sum of the squared residuals, we simply take the error for each point, square it, and take the sum. And that is why it is called the SSR, or the sum of squared residuals. Now, we can actually represent this RSS into another form, and we can compute that from simply taking the dot product of error in a vector with its transpose. Okay, So as you can see here, we have the error, and then we take the transpose of that, and then taking the dot product of this will be essentially equivalent to this formula. Okay, and now the mean squared error is simply the RSS divided by n, which in other words, this RSS may be taken from the dot product of the error vector with its transpose, okay, divided by n, which is the number of samples. Now, this method is called the least squares method, or it's a closed form method that is estimated from the data itself. So it does not change. It will only change if there are differences with the data set. Okay. Now, when estimating the parameters in these squares, we compute this by using this closed form solution. And so we can obtain these vectors of weights beta. Okay. The problem is that in this kind of closed form solution, there is a computation which involves a matrix inversion, and it is a very expensive operation. So suppose we have 100 predictors, and so we need 100 by 100 matrix. And since an inversion requires n cubed operations on average, so as you can see, we take the dot product of these two, invert, and then take the dot product again. So it would require at least 1 million operations to invert the matrix. So it is very expensive. Gradient descent is another alternative that we can use, especially if the data set is large. Okay, and it performs much better in terms of execution times and the number of operations, essentially reducing the cost of the computation. So especially when, of course, we deal with a lot of predictors. And in the real world data, data involves a lot of features, okay? And so this is the gradient descent algorithm. And we have a set of predictors, x sub 1 to x sub j with the bias, assuming its value is 1. And each of this predictor, as well as a bias, of course, has associated weights. All right. And we take the weighted sum of each predictor and the weights. Right. So it is equivalent to simply taking the dot product of the theta transpose and x. Okay. And using this equation or using this weighted sum, we can estimate a certain value y. So we simply have to plug in the x values in the predictor, and then we can obtain a value or our response y. So of course, in order for us to evaluate this procedure, we have to calculate for the cost, and we want as much as possible to minimize that cost. And in order for us to minimize that cost, we have to compute for, we have to estimate the best or optimal weights, right? So we have to iteratively compute for the new weights until such time that we obtain a minimized cost. And in order for us to compute new weights, we can simply do this formula. We have the temp for all of the weights. We simultaneously compute for the new values. We have the theta minus the learning rate alpha times 1 over m, which is m's number of samples. And for all of the sample in the training set, we compute for the error between the predicted and the actual multiplied to the x na predictor, okay? And essentially, this is equivalent to taking the dot product of x and the error, okay? I hope you understood that. So after computing the new weights, we will have to simultaneously update the weights and continue again until such time that we obtain a more minimized result. Okay.